My name's Mike Povey. I'm the General Manager of TLV in UK, and I've been asked to make a presentation on steam trap management and how we manage the steam trap population within various industries. So I'd like to start by asking the question of how is plant steam managed? From our experience, the production process is managed very precisely, but the steam system, I'll say, is often not managed, and I think I'm being optimistic. If we can optimize the steam system, we can generate a significant value by using steam in the most efficient way. If we look at some typical scenes from steam plants, I'm sure all of you are used to this kind of thing with steam wisping out all over the place. The only thing I'd like to say at this point is the more you know about the production process, the more effectively you can actually be utilizing the steam that's available. We often go into sites and be asked to optimize steam systems, look at steam systems, and because we don't know the process well enough, we come up with a standard answer. We do need to tailor those answers to suit the sites that we're working on. The basic fundamentals of steam. We have three things that we're trying to do with a steam system. We're trying to supply dry steam. We want dry steam. We don't want wet steam. Wet steam isn't good at giving up its heat. We want the steam trap to discharge the condensate as it's formed, so it doesn't cause a barrier to be for the heat transfer. And we want the steam equipment always to have steam available to it. By doing that, we increase plant availability, we lower maintenance costs, we don't get the unexpected breakdowns because of failures, and we also increase this energy efficiency. A big block that we find when we talk to customers about this is justifying the expenditure. And I'd like to take a little while just to go through a scenario that's quite common, just to highlight the actual savings that are available by properly optimizing your steam system. So if we start with a plant, typical plant, 500 steam traps, working 24 hours a day, 50 weeks of the year. Steam cost of £25 a tonne. It was a round number, I accept that. And the current failure rate is 22%. Again, the failure rate is our average that we find when we first survey on sites. It's not a made-up figure, it's not a high figure. In that situation, the steam losses will be just over £115,000, just on wasted steam. If we optimise that system properly, we can get the failure rate down to 6%, less than 6%. By doing that, the losses fall as well to somewhere about 30,000, which is basically a benefit of £84,000. That's a pure financial benefit. We're not looking at the other benefits of better reliability, better availability of plant, and more effective heating. So on top of that, maybe every shift we could do one more batch process. The reason we came up with less than 6%, we have experience over 15, 20 years, and these are actual figures where we've looked at the first survey failure rate down to after 5 years. By trying to optimize the steam system, by looking at the bigger picture, rather than just repairing the steam traps that have failed, trying to work out why they failed, how we can make the system better. What I would like to do is just touch on some different testing methods to highlight reasons for using, I'll say the best, but the more comprehensive systems. Some people say, well, we can just look at the trap and tell whether it's working or not. I'm very impressed. Most traps have an inlet pipe and an outlet pipe. Unless there's steam actually coming physically out of the trap body, I don't know how you're going to tell anything. But some people still say that's the best way. We can use thermographic inspection. We can look at the temperature. We know the temperature of the steam that should be present. If we look at the temperatures, if on the inlet or outlet it's a very low temperature, it will imply that the trap is blocked. Okay? If there's a high temperature on the outlet side, it may be that the trap has failed open, maybe, but it is very subjective. It depends on how we're interpreting those pictures. Also, the estimation of any losses is not the most accurate. We also could do it using ultrasonic only, have an ultrasonic gun, listen to the noise. We can pick up cold traps, leaking traps. We can tell that the trap is leaking, so we know whether it's good or bad. But it does rely on the inspector to be experienced and be able to interpret that noise. The noise also varies for the same type of trap, same pressure, depending on where it is actually located. It will make a different noise. So you have to be very experienced to be able to do it. Again, the loss estimation is an estimation. It's not particularly accurate. Another way of doing it is to actually combine temperature and ultrasonic, so have it in a single unit so we can detect very clearly the block traps. We can also detect the leakages. There are systems available that have it all built into a computer-based system. The advantage of that is it removes the subjectivity. The inspector doesn't have that much of an input into what the numbers actually read. It is a very judgmented, quantitative amount. The estimation, because of that, it's referring to stored records, is very accurate. It also enables, because it's already automatically into a database, we can present the results instead of a tabulated Excel sheet. We can present the results as a map, and that's something that we're doing very actively because we can see a big benefit to it. So we have a plant map with all the trap icons located on it. Green obviously is good. Red and yellow are leaking, so there's a problem, you've got a loss there. But also the block traps and the not in service traps. The big advantage of this is it means you can visualize the problems. So on this graph, you can see in the center there's a block of red. It may well be the traps themselves are actually a good trap for that location, but the location has a problem. Maybe the steam line feeding into it is an old pipe that rust is coming off it, and that's causing problems. So it enables you to identify areas of concern that you can look at in a separate detailed survey. The other thing we can do with that data is obviously look at it over a period of time. So on this map, it's based on historical data. There's an area that has more failures. Again, it's not the trap that's at fault, it's the system around the trap. By putting it graphically, it enables you to see that a lot easier than having an Excel sheet with 5 years worth of history for locations. We believe that unless you can see the problem, you can't fix the problem. The other thing I want to talk about is trap selection. We need to use the right trap in the right place. A trap has a life cycle. Initially, we start and we buy the trap and we install it. Then we use it. All traps have a leakage, an inherent leakage in their operation. Some are more than others. At the end of the cycle, the trap's failed, we've got losses now. There is a problem there. And the cycle keeps repeating. As I said, the operational losses are different from different traps. So a thermodynamic trap, a disc trap, because of its operation, it's very pulse operated. You'll always get at the end of each cycle a little puff of steam. That equates to about 1 kilo an hour. If you have a mechanical float trap, free float, I'm TLV, I'm sorry, the orifice is underneath water level, so it's very unlikely, if the trap is operating correctly, that you'll have a steam leakage. So the operational steam losses are less. If we look over a life cycle cost, what we're trying to show with this graph is that buying a cheap trap is not necessarily the cheapest way of doing things. You can see on the graph, the left-hand most trap is more expensive to buy, but it lasts longer, it has a lower functional steam loss, so over a 10-year cycle, it's actually cheaper than the far right trap, which is only it's cost a quarter of the price to buy, but it fails maybe 3 times in that 10-year cycle, 4 times. So you have to buy 3 or 4 replacements and fit them, and you have the losses of when it failed, you've got a large steam loss. So the cycle cost is more important in our eyes than actually the purchase price. What next? I'd like to say the answer is TLV. I'm not being honest if I say that. The biggest thing that we've found in having a successful trap management within any scenario, there are a few things. You've got to undertake regular surveys. It's no good doing one survey and saying we're really good at it. You've got to do regular ones, depending on your industry, depending on your steam costs and the situation you're in. It may be annual surveys. Some sites like doing twice a year. Every 6 months they'll do a survey. The other thing is when you've identified the leaking traps and the block traps, something that a lot of people don't do, you need to replace them as soon as possible. It's no good testing it and taking a year to change the traps, which we do have customers who do that. You also need to correct the problem. It's no good just changing out like for like. Is it the right trap? Is the trap installation correct? Do we have the blow-off valve to get rid of the dirt before the trap? Are we collecting dirt in that trap rather than emptying the condensate? So we need to look at the steam system as a whole rather than isolated steam traps, and we need to do the improvement. The thing that I would like to say is most critical, though, is the last point. For a trap management program to be successful, everybody within the company needs to buy into the idea of we are trying to save energy. We are trying to make our process as efficient as possible and want to make it succeed. If you have a fitter who's not bought into the idea, the traps won't get changed out. If you have an energy manager who plays at the idea of liking it, it won't work. You need that buy-in from all levels of the company.